we're going to solve a more complicated second-order linear constant coefficient non-homogeneous initial value problem. As usual, we're going to start by solving the homogeneous differential equation. That differential equation right there we solved by making an educated guess, e to the RT. When you plug that into the differential equation, you end up getting r squared minus 2r minus 3 equals 0, which can be factored, giving us two solutions, linearly independent solutions, to the homogeneous differential equation. So the solution to the homogeneous differential equation, it's also called the complementary solution, is c1 e to the 3t plus c2 e to the negative t. Now this is not the general solution to this differential equation because this differential equation is non-homogeneous. Now we want to find a particular solution to this differential equation, so we make an educated guess. In this case, the guess would be a e to the 3t plus b cosine of 2t plus c sine of 2t. But whenever you make a guess like this, you have to check to make sure that none of these terms in your particular solution appear in the homogeneous part of the solution. In this case, we do get a homogeneous term appearing in your particular guess. So we learned the rule in class. You actually have to multiply that guess by t, or at least just that part of the guess. Alright, so we're hoping that this is going to solve our differential equation, but we're going to need to find the a, b, and c values that work with that non-homogeneous dE, so we need to take two derivatives. So now we want to take our guess and its two derivatives and plug all of that into our original differential equation. Let's do it. Okay, that's a whole lot of equation. We need to group some terms together and cancel out what we can. One thing you'll notice is that we don't have a t, e to the 3t term on the right side, so hopefully we won't on the left side either. Let's see. We have a 9a term here, minus 6a, minus another 3a. So actually all of the t, e to the 3t terms cancel out, as they should. And now it would be really nice if we could group all of the e to the 3t terms together, all of the cosine terms together, and all of these sine terms. Now we can simplify and combine like coefficients, I suppose, here. So we've simplified all of the terms on the left side now, and now it's a matter of matching up coefficients on the left-hand side with coefficients on the right side of the equation. So right here we have that 4a is 4. Okay, that worked out pretty nicely. If we match up our cosine terms, we have negative 7b minus 4c equals negative 5. And if we match up our sine terms on the left and the right, we have 4b minus 7c equals, well, there's no sine term over here, so it must just be a 0 term. Obviously, a just equals 1. That's the easy one. And now we have two equations and two unknowns to solve here. This, unfortunately, is going to involve some fractions. I'm going to take the green equation here, and I'm going to multiply it by 4. And I'm going to take the red equation, and I'm going to multiply the red equation by 7. The reason I do that, of course, is because if we add the two equations together now, we eliminated the b term, and we should be able to solve for c pretty easily. If we do that, I'm getting negative 65c equals negative 20. Hopefully I haven't made any mistakes. And you get c is 20 over 65, which reduces. Now we can take that c value and plug it into either equation. I'm going to use this one right here because this is easy to solve for b. Okay, so what did we do so far? So far we solved our homogeneous differential equation. Found it right here. And we made a nice guess for a particular solution right here. And then we found the a, b, and c values that make that particular solution work. So if I write it down again, our homogeneous solution was, if we plug our a, our b, and our c into our particular solution, we get a particular solution that looks just like this. And now we add these two homogeneous and particular solutions together to get the general solution. And you're feeling pretty happy, you're feeling pretty satisfied with yourself with that general solution there. But don't forget, we have a little ways to go here. We actually were given initial conditions in this problem. So we need to, at this point, find the C1 and C2 that satisfy those initial conditions. Note that you don't want to plug your initial conditions into just your homogeneous solution because that doesn't solve your differential equation. This one, this general solution, has both the capability of solving the differential equation and satisfying the initial conditions. So I wrote down the initial conditions right here. Obviously, we're going to need to take a derivative of this general solution at some point, so I'll just do it now. Now we can plug our first initial condition into y of t. We can plug our second initial condition into y prime here. Now we can simplify, and ultimately we have two equations and two unknowns here. We have c1 and c2 that we don't know, and two equations. So I got negative 60/13 by starting with negative 3, subtracted 1, and I got negative 4, and then I also had to subtract 8/13, and I kind of wrote my work in over here. Hopefully I didn't make any mistakes. I don't have a whole class checking my work on this, unfortunately, so hopefully I didn't mess anything up. Alright, we're still solving for c1 and c2. Obviously at this point we can take these two equations and add them together, and that would eliminate c2. I get 4c1 is negative 54/13, and if we divide both sides by 4, I believe you get negative 54/52, which reduces to negative 27/26. My goodness, this problem is extra satisfying. We can use the first equation up here, solve for c2. And again, if I haven't made any mistakes, it does reduce. 13 cancels, strangely enough. And you just get c2 is regular old 3/2. All right, we did all this work. Let's write down our final answer. There it is. I just copied down our y of t, and I plugged in c1 and c2 here. Let's hope it's right, and I didn't embarrass myself publicly on YouTube. And let's get you a video quiz. Here you go. Solve this initial value problem. There it is. Don't forget to plug in your initial conditions when you find your general solution. Good luck, and I will see you in class.